In the name of Allah. In this lecture, we will discuss a very important topic, which is the phenomenon of skin effect and its severity when harmonics are present in the electrical network. This combination leads to a significant increase in electrical losses and causes the temperature of electrical equipment to rise to completely unacceptable levels. It is commonly stated that one of the biggest problems caused by harmonics in the electrical network is the overheating of electrical equipment such as transformers and cables, in addition to the high temperature experienced by various devices and loads such as electric motors. In some cases, these harmonics can ultimately lead to the complete failure of transformers and motors. Unfortunately, many engineers observe that electrical equipment is operating at extremely high temperatures, but are completely unaware of the role and danger of the skin effect when harmonics are present. As a result, the fault diagnosis is often incorrect. Therefore, in this lecture, we will thoroughly explain and analyze the seriousness of the skin effect in the presence of harmonics, and we will also discuss how to properly address and mitigate its impact. Of course, everyone knows that the flow of alternating electric current in any conductor generates an alternating magnetic field. This means that the occurrence of magnetic flux or the magnetic field is directly associated with the flow of electric current in any conductor. It is important to understand that the deeper we move toward the interior of the conductor or the core of the conductor, the greater the magnetic flux becomes inside the conductor. Of course, the increase in magnetic flux is associated with an increase in inductance, and we all know that the inductive reactance, which is denoted as XL, is equal to 2 pi FL. This means that the more the inductance increases, the inductive reactance will increase accordingly. We also need to understand that, according to the equation in front of us, an increase in frequency also leads to an increase in inductive reactance. This means that the deeper we go into the conductor or the core of the conductor, the inductance increases, and consequently, the inductive reactance increases as well. We need to understand that the increase in inductive reactance inside the core of the conductor causes the alternating current to be pushed out from the inside or core of the conductor so that it flows through a certain layer near the external surface of the conductor. This means that the electric current concentration will be on the surface or in the outer layer of the conductor's surface. As we can see, the areas where the alternating current flows are shown in red, but inside the core or middle of the conductor, the alternating current flow is almost negligible or passes at very, very low values. This phenomenon is called the skin effect. Therefore, the skin effect is the flow and passage of alternating current in the outer limits or outer layers of the conductor's cross-section with much greater values than its passage in the middle or core of the conductor. As we said, this happens for two reasons. The first reason is the presence of inductance, and the second reason is the presence of frequency, which increases the inductive reactance inside the core of the conductor, thus pushing the alternating current to flow in the outer layers of the conductor's surface. This means that the influencing factor on this phenomenon is the presence of the frequency value, meaning that as the frequency increases, the skin effect phenomenon also increases accordingly. Consequently, the current will pass through a thinner thickness or a thinner outer layer of the conductor due to the increase in frequency. It is very important for us to understand together what causes can lead to an increase in frequency. Of course, there is nothing other than harmonics. As we know, electronic devices, factories, and welding workshops, for example, are among the main sources of harmonics in the electrical network. Everyone knows that harmonics are different frequency components within the voltage and current waveforms. This means that if the fundamental frequency of the network is 50 Hz, then there will be multiple harmonic frequencies that are integer multiples of 50 Hz. For example, if the electrical network contains a third-order harmonic, this means the frequency present is 150 Hz. If the network contains a fifth-order harmonic, this means the frequency present is 250 Hz. If the network contains seventh-order harmonics, this means the frequency present is 350 Hz, and so on. Various frequency values due to the presence of harmonics. As we see, the more harmonics increase, the higher the frequency values will be, and consequently, the skin effect phenomenon will also increase. This means that the tendency of the current to be expelled to the outer layer of the conductor will increase. So, Is it really possible for harmonics to exist in the electrical network or AC circuits with orders higher than the third, fifth, or seventh? Of course, definitely yes, they do exist. As we can see before us, there is a real practical image of the harmonics present on an 11 kilovolt voltage cable. In the previous example, we talked about harmonics of the third, fifth, and seventh orders, but imagine here that there are harmonics ranging from the second order up to the 50th order. Imagine the shape of the skin effect phenomenon in the conductor or cable carrying an alternating current at a frequency of 50 Hz along with harmonic frequencies from the second order up to the 50th order across the three phases. As we said, the more harmonics increase, the higher the frequency will be, and consequently, the skin effect phenomenon will increase. Of course, the increase in the skin effect means an increase in the expulsion of the current to flow in the outer layer of the conductor. So, how can we explain this? For example, if we have 5 copper conductors named A, B, C, D, and E, all with the same cross-sectional area, let's say 300 square millimeters, and approximately the diameter of the conductor in this case is 20 millimeters. As we can see, conductor A is used in direct current DC circuits, which means the frequency is of course 0. Conductor B is used in alternating current AC circuits with a frequency of 50 Hz. Conductor C is used in AC circuits with a frequency of 60 Hz. Conductor D is used in AC circuits with a frequency of 1 kHz. Finally, conductor E is also used in AC circuits with a frequency of 10 kHz. The question here is, we want to understand the shape or distribution of the alternating current in each conductor according to the skin effect phenomenon, naturally considering the different frequencies for each conductor. As we can see, conductor A is used in direct current DC circuits, which means that the current passing through conductor A is a direct current. Therefore, since it is direct current, the frequency will be 0. Given that the frequency equals 0, and according to the equation for inductive reactance equals 2 pi FL, the inductive reactance will be 0. Consequently, there is no reactance or impedance inside the conductor. This means that the skin effect does not exist or is negligible. Thus, the direct current will flow through the entire cross-sectional area of the conductor, as we can see with the current shown in red. But in the case of conductor B, this conductor is used in alternating current AC circuits with a frequency of 50 Hz. Therefore, since there is a frequency or alternating current, the skin effect will be present. Accordingly, based on the equation inductive reactance equals 2 pi FL, there will be an inductive reactance XL of a certain value. This means that the presence of inductive reactance will cause the alternating current to be pushed from the core or inside of the conductor towards the outer surface or the outer layer of the conductor. In other words, the alternating current at a frequency of 50 Hz will flow and move through a certain thickness of the outer layer of the conductor, approximately 9.5 millimeters. Consequently, the cross-sectional area of the conductor through which the alternating current will flow is about 227 square millimeters, not 300 square millimeters as in the case of direct current. Let us focus on this point because it is very, very important regarding conductor C. As we can see, conductor C is used in alternating current circuits with a frequency of 60 Hz. This means that the inductive reactance XL will increase to a value higher than the value at 50 Hz due to the increase in frequency. The slight increase in the value of XL will cause the alternating current to be pushed further toward the outer surface of the conductor, slightly more than in the case of 50 Hz. Therefore, the alternating current at 60 Hz will flow through the outer layer of the conductor with a thickness of approximately 8.5 millimeters, which is less than the thickness at 50 Hz. Consequently, the cross-sectional area of the conductor through which the alternating current flows at 60 Hz will be about 210 square millimeters, which is less than the cross-sectional area at 50 Hz. Hence, this important point must be emphasized. It is not correct to perform electrical calculations while completely ignoring whether the frequency is 50 Hz or 60 Hz. In other words, the cable catalog from which we select the appropriate cross-sectional area must specify the frequency for which the catalog data applies, whether it is 50 Hz or 60 Hz, because the cross-sectional area calculated in the catalog is based on a specific frequency value. Of course, if it is calculated based on 50 Hz, it will be different and not valid for a 60 Hz system. The same applies to conductor D with a frequency of 1 kHz. Of course, as the frequency increases, the skin effect phenomenon will also increase. Consequently, the thickness of the outer layer of the conductor through which the alternating current passes will decrease. This means that the alternating current at a frequency of 1 kHz will flow through an outer layer thickness of approximately 2 millimeters. Therefore, the cross-sectional area through which the alternating current passes at 1 kHz frequency will be about 60 square millimeters. In the case of conductor E, with a frequency of 10 kHz, the alternating current will flow through a thickness of the outer layer of the conductor not exceeding 0.7 millimeters, meaning it will flow through a cross-sectional area of approximately 21 square millimeters. So, as we can see, the higher the frequency, the greater the skin effect phenomenon becomes, which leads to increased displacement of the alternating current toward the outer layer of the conductor. As a result, the cross-sectional area and the thickness of the layer through which the alternating current flows will decrease. However, it is very important to clarify a critical point. Suppose a cable with a cross-sectional area of 300 square millimeters is used in a circuit carrying a load of 500 amperes. Naturally, to select a conductor or cable cross-section capable of carrying 500 amperes of alternating current, we refer to cable tables. We find that, for example, a cable or conductor with a 300 square millimeter cross-section at 50 Hz can carry 500 amperes of current, but at 50 Hz only. This is because the cable manufacturer has made calculations considering the skin effect and knows that the current will flow through a specific layer of the conductor's surface. In other words, the 500 amperes will flow through the outer layer of the conductor or cable, which is about 227 square millimeters in cross-sectional area. Now, what is the problem here? The issue arises when the same cable with the same cross-sectional area is used to carry the same current value but at a frequency of 60 Hz. In this case, the 500 amperes will no longer flow through an area of 227 square millimeters, but instead through an area of only 210 square millimeters. The same applies if the same cable is used at even higher frequencies. For example, when harmonics are present, then the 500 amperes would be forced to flow through a cross-sectional area as low as 60 square millimeters, and so on. This, of course, leads to cable overheating and eventually cable failure. The important and most critical point in this topic, as we all know, is that the resistance of any conductor is calculated using the relation R equals rho multiplied by L divided by A, where R is the resistance, rho is the resistivity of the material, L is the length of the conductor, and A is the cross-sectional area. This means that the resistance of the conductor is inversely proportional to the cross-sectional area. In other words, if the cross-sectional area of the conductor decreases, the resistance of the conductor will increase. If we refer back to the previous examples concerning conductors A, B, C, D, and E, we want to determine the cross-sectional area of each conductor and its corresponding resistance. It is essential to understand that the area and resistance are not calculated based on the total cross-sectional area of the conductor. That is, the resistance here is not calculated assuming the full area of 300 square millimeters, but rather based on the actual area or thickness of the layer of the conductor through which the electric current flows. From this, we understand that although the total cross-sectional area of each conductor is 300 square millimeters, due to the different frequency values for each conductor, the thickness of the outer layer of the conductor through which the alternating current flows will vary. As a result, the actual cross-sectional area for current flow decreases with increasing frequency, leading to an increase in resistance. That is why we find that in the case of conductor A, which is in the case of direct current, the total cross-sectional area is 300 millimeters squared, and the actual cross-sectional area through which the electric current flows is also 300 millimeters squared. However, in the case of conductor B, which is an alternating current at 50 Hz, although the total cross-sectional area is 300 millimeters squared, the actual cross-sectional area through which the electric current will flow is only 227 millimeters squared. As for conductor C, which is in the case of alternating current at 60 Hz, the actual cross-sectional area is 210 millimeters squared. In the case of conductor D, with a frequency of 1 kilohertz, the actual cross-sectional area of the conductor is 60 millimeters squared. And in the case of conductor E, with a frequency of 10 kilohertz, the actual cross-sectional area is 21 millimeters squared. And as we have said, the resistance of the conductor is inversely proportional to its cross-sectional area. And as we can clearly see, the cross-sectional area decreases as the frequency increases, which leads us to understand that the resistance of the conductor increases as the frequency increases. Therefore, the resistance of conductor E, which is the conductor operating at a frequency of 10 kilohertz, will be the highest possible due to the increase in frequency. Now, what are the technical problems that can occur as a result of the increase in the resistance of the conductor? Let us start with the less critical problems, although in reality, these are still very serious problems. The first problem is the issue of power losses. And of course, electrical power losses are calculated using the formula power loss equals 3 times the square of the current multiplied by the electrical resistance. So, when the resistance of the conductor increases, the value of the electrical losses also increases. And that leads to very significant and costly losses. That's why it's absolutely essential to avoid an increase in harmonics, because that helps prevent the increase of the skin effect. And by doing so, we avoid the rise in the conductor's resistance and in turn avoid the increase in electrical losses. The second problem that we will face due to the increase in the resistance of the conductor is the voltage drop. As we all know, the voltage drop is equal to the electric current multiplied by the resistance of the conductor. Therefore, an increase in the resistance of the conductor means an increase in the voltage drop. Naturally, if we have an overhead line or an electrical cable over a very long distance, this means that the voltage at the end of the line will be lower than the required and appropriate value for the electrical loads. And of course, this happens due to the decrease in voltage resulting from the voltage drop. Because clearly, the longer the conductor or the transmission distance, the greater the resistance will be, and thus the voltage drop will increase. This means that the voltage reaching the end of the line will be at a value that is completely unsuitable and unacceptable for the electrical loads. One of the most important and dangerous problems caused by the skin effect, especially in the presence of harmonics, is the rise in temperature and overheating of electrical equipment such as transformers, cables, distribution busbars, overhead transmission line conductors, and the damage and failure of various devices and loads, most importantly, electric motors. As for transformers, for example, we may notice at some point that the temperature of the transformer rises to an unacceptable level. With continuous monitoring, we find that the temperature is continuously increasing. Naturally, the transformer is taken out of service in order to determine the cause of the temperature rise. All required maintenance procedures and necessary tests are performed. Unfortunately, after reconnecting the transformer, we discover that the high temperature is still continuously increasing, despite having carried out all the maintenance and tests on the transformer. Supposedly, there should be no obvious reason for the temperature rise. So, what is one of the possible causes of this problem? Without a doubt, there are many faults that could lead to an increase in the temperature of the transformer, and one of the most important is the phenomenon of the skin effect. It is also important to know that one of the main causes resulting from the presence of the skin effect phenomenon is the increased rise in the temperature of cables, which ultimately leads to the failure of the cables. According to the previous explanation of the skin effect phenomenon, this is due to the electric current passing through a cross-sectional area smaller than the required area. This occurs because of the increase in the skin effect, which reduces the effective cross-sectional area required due to the increase in harmonics and varying frequencies. Therefore, it is very important to avoid the increase in harmonics and consequently the increase in frequencies and thus the increase in the skin effect phenomenon. Certainly, the skin effect phenomenon will also affect electric motors and cause an increase in the temperature of the motors, which may ultimately lead to the complete failure of the motors. For example, we have a motor operating at a frequency of 50 Hz, and let us assume, for example, that the rated current of this motor is 71 amperes. And let us assume, for example, that there is another motor, but it operates on direct current, and its rated current is also 170 amperes. Since it is direct current, this means that the frequency in this motor is 0 Hz. Therefore, it is very important to know that according to the previous explanation and according to the skin effect present in alternating current and according to various calculations, we find that the appropriate cross-sectional area for the motor operating with alternating current at 170 amperes is a cross-sectional area not less than 50 square millimeters. Also, according to the previous explanation, we find that the appropriate cross-sectional area for the motor operating under direct current, DC, with a rated current of 170 amperes is, for example, 35 square millimeters. Therefore, from the previous explanation, we find that the cross-sectional area used in the case of the motor operating under DC is certainly less than the cross-sectional area used for the motor operating under alternating current, AC, at 50 Hz. Hence, we emphasize that it is very important to know the values of harmonics present in the electrical network to avoid high frequencies, thereby avoiding the increase in the temperature of the conductors and consequently preventing their failure. But the point that concerns us most in the end is that the skin effect phenomenon exists as long as there is alternating current. However, the increase in frequency is a very serious problem because it causes an increase in the resistance of the conductors, a rise in their temperature, overheating of electrical equipment, and possibly their failure. Therefore, as much as possible, we should overcome the skin effect phenomenon by addressing the harmonics present in the electrical network, thereby reducing electrical losses as much as possible. Thank you for your attention. See you in the next lecture.